Okay, so today we're talking about sources of magnetic fields, and I forgot to push the record button. So we first talked about sources of electric field, which we know from our work previously in this course, that's due to charges, right? And even if we have a situation where there's no net charge here, like a dipole, we still have electric fields. But we know that there's no such thing here as magnetic charge from the last chapter. We discussed kind of what looks like Gauss's law for magnetic fields. The net magnetic flux through a closed surface is always equal to zero. And there's no experimental evidence to suggest otherwise. Okay, and so we can't have a situation here on the right where we have some kind of magnetic charge and it's generating this magnetic field around it. Remember, magnetic field lines always have to go around in a closed loop. They always wrap around on themselves. Okay, and so what is the source of magnetic fields? Moving charges or currents. Those are the sources of magnetic fields. Okay, so what is the magnetic field of a moving charge? So what, and maybe I can just type this question out. So the natural question to ask now is, what is the magnetic field of a single moving proton? Okay. Well, this is something that has to be experimentally determined at this stage, right? In the future, once we've established all four of Maxwell's equations, which, you know, even in a class like this, it tends to be more of like an upper division task to take Maxwell's equations and then solve them out. But it's maybe something we can take a look at. So for now, we have to have kind of an empirical approach. What does experiment tell us? An experiment tells us that the magnetic field of a proton moving with constant velocity is some constant. This is the constant piece. So this is the constant that fixes the units. Talk more about why it's divided by 4 pi here in a minute. It depends on the charge, and so if this is really a proton, we use the symbol E for that, right? And then the velocity of that charge, and remember, this only applies when the velocity is constant. We'd have to make corrections if there was an accelerating charge. Then there's this cross product in here, cross a radial unit vector. We'll get a picture to explain exactly what that means. And then, of course, like we always see with gravity, with for Newton's law of gravity and the Coulomb's law, it's always over it's always over r squared, right? 1 over r squared dependence. Okay, so let's get a picture here. So suppose we have some axes here, and we're going to really take advantage of the dot and cross notation that we used last time. Remember, dot means, from your guys' perspective, coming out of the screen, and cross means going into the screen. Okay, so suppose we have a moving charge here. Maybe we'll just plop it on the origin like so, and it's moving with a velocity v here like this. And we want to know, what is the magnetic field at some point over here? Well, the distance from the charge to that point is the vector r. So that's the vector r there. And so the unit vector, r hat, is this vector right here. Okay. And we need to know the direction of the magnetic field from v cross r hat. Okay. You can use the right-hand rule to get the direction. First get your right hands out. Okay, this is my right hand right here, so hopefully you guys can see this is my right hand. Sometimes it's mirrored. Take your thumb and stick it in the direction of V. So for me, I have to turn all the way around like this, right? So now my hand is like this. My thumb is in the direction of V, and I can curl my fingers around, and I hope you guys can see that on top of my thumb there, the magnetic field would be coming out of the screen. I'll go ahead and go full screen here in a second. I'll show that again to make sure you guys see that. So the magnetic field at this point here is coming out of the screen. I'm just drawing it a little to the side so it doesn't get too cluttered here. I'll give you a second to copy that down, okay, and then I'll full screen and I'll show you again the right hand rule there for that. I'll give you like 5 more seconds. Okay, I'm going to stop the share, but I'll share it again in a second. Okay, so hopefully you guys can see me full screen now. So my thumb here, I want to point that in the direction of V, and you guys can already see my fingers are curling around this way, right? So at the top, my fingers are coming out of the screen, right? So we use a dot to indicate coming out. Okay, so we'll go ahead and share back now. All right, so any questions up to this point here? Anything that we need to hone in on? Give me a thumbs up if you're ready to go. Okay. So I believe we have this example now. So I'm going to go ahead and throw an example up for us to work on. Okay. I'll go ahead and type out the question here. So we have 2 protons, and let's go ahead and make it black, not green. We have 2 protons moving parallel to the x-axis. See figure. Okay. They have the same speed v, and we want to know what is the direction and magnitude of the electric and magnetic forces acting on the top proton, and what is the ratio of the electric force to the magnetic force. Okay. So while you guys are copying that down, I'm going to go ahead and simplify that out a little bit for us here. So break it down into parts here. So part A is, let's take a look at the direction first. So what are the directions for FE? And you can see on the figure they're already labeled there, but really don't cheat, really use the right-hand rule to verify the direction of the magnetic force. I think we all know the electric force is repulsive, right? But maybe we don't necessarily know the magnetic force is repulsive. So pretend like you don't see it there in the figure. So directions for FE, and they call it FB. I tend to use the letter M for magnetic, but whatever you're comfortable with, you can use FB, FM. And then maybe part B here would be the magnitude part. So what are the magnitudes of FE and FB or FM? And then finally, for the last part, I'm going to calculate. Let's actually make it the magnetic force over the electric force. It's really the same ratio though, one over the other. Okay, so that is the task here. Now, since it is the first example here, maybe I'll work through this one with you guys. So who can tell me, maybe you can write it in the chat or you can just speak up. Who can tell me the direction or how we find the direction of the electric force? Just a quick little explanation. Just to make sure we remember what happened 3 or 4 chapters ago. So you can give your answer in the chat or you can speak up here. So we're talking about the electric force here. Shouldn't be taking this long. We have two positive charges. What do like charges like to do? What kind of force? Attractive or repulsive? There we go. Okay, here's the answers we're looking for. Repulsive force, right? So the force is going to be directed away from the other charge. So since we're interested in this charge right here, well, the repulsive force then is going to be away from this charge down here. So it's pointing in the positive y-axis according to the diagram there. Okay, good. Now, how about the direction of the magnetic force? Well, that one may be a little bit trickier. So let's go ahead and write out what the magnetic force is. Remember from the Lorentz force law, the magnetic force is QV cross B. And so in order to figure out the direction of the magnetic force, we have to know the direction of the magnetic field, right? Now the magnetic field has been given to you here in this diagram because we just kind of presented experimentally how to get the direction of the magnetic field, right, from this expression here. But you can see, again, we could use the right-hand rule. If we had a proton moving in a certain direction, we can get its magnetic field. So let's go ahead and practice that real quick. So the bottom charge here is the one that we're interested in. This is the motion of the charge, or excuse me, this is the charge that's generating the magnetic field up here, right? So what direction is that charge moving? Well, it's moving to the right on your screen. So get your hands up, your right hands, and stick your thumb in the direction of the motion of the charge, right? So point your thumb to the, point your right thumb to the right. So you have to contort your arm a little bit for that. And then your fingers are curling away from your screen, right? So that's what they've indicated here with the blue vector. So that's coming out at us along the z-axis. Okay, good. So now we know the direction of the magnetic field there by the right-hand rule. Now we can get the direction of the force by the right-hand rule again. So we now need to use our other right-hand rule, which is to stick our fingers in the direction of the first vector. Let me go ahead and use a color here. So stick your fingers in the direction of the velocity of the charge you want to know the force on. Fingers in the direction of the charge you want to know the force on, in the direction of its velocity. So for me, it's like this, to my left. So I put my right hand fingers to the left, and then I curl those fingers out of the screen like this, because the magnetic field is in that direction. So V cross B, and my thumb is pointing up. Okay, so I can't see any of you, none of you are sharing your video, so hopefully you're using your right hand, fingers in the direction of V, and then curl your fingers towards B. Okay, so you can even write that too, it's always good to write that. So fingers here, and then you curl them in this direction, and then your thumb points in the magnetic force direction. Did somebody turn their video on? Did they want me to check?
My nephew turned a video on, sorry.
Can you say that again? I couldn't hear you.
My nephew turned a video on, sorry.
Oh, you don't have to say sorry. I wish everybody would have their video on so I could actually see if you guys are doing it right, but okay. Oh, okay. I see your situation. Yeah, if you want to use the thing with the 3 fingers, you just have to remember to put your index finger in the direction of V and your middle finger in the direction of B. So if you want to do it, then it would be like this for me. So you make your middle finger come out of the screen. So turn your hand more so your middle finger comes out of the screen. No, it's got to come out of the screen. Your middle finger. So point it away from your screen. There you go. Now you're doing it correctly. You had the right answer for the wrong reason. Okay.
Sir, are you talking about the upper charge, the velocity of the top charge versus the bottom one?
You've got to use the velocity of the charge you're interested in knowing the force on.
Okay.
So that's maybe a good clarification. So this velocity right here is velocity of charge that has Fm acting on it. Okay, it's got to be the one that's moving in the magnetic field. So the bottom charge causes the magnetic field at the top charge. The top charge experiences a magnetic force due to its motion inside the magnetic field that's there because of the bottom charge. Does that make sense? So we can maybe...
Yeah, I was just confused. I thought you were talking about B in the bottom charge. And I was like, hey, where's the force going with this one?
Yeah, so you have to be careful. You got to make sure that it's the velocity of the charge that's going to experience that force. And the charge that's going to experience that force is the charge that's moving in the magnetic field that you've jotted down. So we jotted down this one, and this is the guy that's moving in that field. So that's the one that you have to do V cross B for. Any other questions about that? Okay. Yeah, give a thumbs up if you're good on that. We can go to the next part. Okay, looks good. All right, so now let's review here, right? Coulomb's law. What's the magnitude of that electric force? Right, there's like a constant, right? Coulomb's constant. You guys tell me the other parts. We have Coulomb's constant, that's something over something, right?
Q1 times Q2.
Yeah.
And
Q1, Q2. And then what?
R squared? R
squared, exactly. So Q1, Q2 over R squared. And we could even clean that up a little bit. The problem does tell us that it is 2 protons and the charge of the proton is E. Just to remind you, maybe up here at the top, E is plus 1.6 times 10 to the minus 19 coulombs, right? So if we want charge of electron, we put minus E. All right, now the magnetic force magnitude, that was what we just kind of wrote down as an empirical result. So maybe it's too early for me to ask if you remember, but let's see, does anybody remember without looking in their notes? You can kind of get it from right here. The magnitude, if you remember how to take the magnitude of a cross product. So certainly the charge there is going to be E. So Q is going to be E here. Magnitude of V cross B. So maybe it's something you kind of want to remember it. Keep it in the back of your mind. It's the magnitude of the 2 vectors times the sine of the angle between the 2 vectors. So in this case, the angle is going to be 90 degrees. Maybe I'll use another color here. Let's use pink. So over here on the diagram, the angle between those 2 vectors is 90 degrees. And so the sine is 1, right? So EVB for the magnitude. Well, the story doesn't end there because we just discovered the magnetic field. By the way, I just noticed that chats. Yeah, so good, KQQ over R squared. So we just figured out that whoops, let's go back to black now. We just figured out that the magnetic field of a point charge goes like this constant mu naught over 4 pi times Q V, and it's V cross R hat, right? V cross R hat. We'll go ahead and get the vectors in here to start. And divided by R squared, that 1 over R squared behavior. So this is what we just saw, right? So start committing it to memory. But let's take the magnitude of this now. So if we want to take the magnitude of this, if B on the left side, what do we have on the right side? Well, mu 0, 4 pi, doesn't change, right? Q is E, right? We have Q is E, the charge of the proton. So put that in there, E. And then we've got to take the magnitude of V cross R hat. We can use the same trick that we did over here. Let me highlight in red. We use the same trick that we did right here. The magnitude of a cross product is the vector's magnitude times the other vector's magnitude times the sign between them. So V, and then magnitude of R hat is 1. Remember that, guys? R hat has magnitude of 1. That's a unit vector. So that one doesn't even show up. And the angle between the velocity and R hat, probably need to get a new picture going here, but the velocity that we're interested in, you may get the right answer for the wrong reason here. It's not this velocity right here. It's not this one. It is the velocity of the guy up here. Oh, excuse me. No. Wrong. I'm wrong. I can make mistakes too. No, it is this velocity actually, because this is the velocity that generates the magnetic field. Sorry about that. So this velocity is in this direction. R hat is in the vertical direction, right? And so the angle here is 90 degrees. So the sine theta is going to be 1 again. Sine theta is 1. Okay. And we're forgetting R squared now. So let's divide by R squared. Magnitude of R squared is just R squared, right? It's already a magnitude. Okay. Okay, does everybody understand this little bit right here? The V cross R hat there. So it's this velocity here crossed with this radial vector there. So magnitude of V times magnitude of R hat times sine, which is 1. Okay, let me know if there's a question. So we got the magnitude is mu 0 E over 4 pi R squared, and then don't forget the V. Okay, that's B. Again, we got to go back and plug it in up here. Okay, so one more step before we're done with the magnitude of the magnetic force. So I know this part is the long part here. After this, things get a little bit easier to follow. So let's go ahead and do it in blue here. So the magnetic force is EV, so that's the first two terms there. So that's the first two terms. And then now we got to plop this magnetic field in here. So mu 0 EV over 4 pi R squared. So simply just plugging in this magnetic field that we have here in for B up here. Maybe let's highlight again. So now we're plugging in for B here from this expression right here. We're plugging that in right here. Okay. All right, so let's group up some like terms here. So it's going to be mu naught over 4 pi. Let's bring that piece out to the side. And we have an E squared and a V squared and an R squared. Okay, so E squared, V squared, R squared there. And then this is just the constant piece. Right, and then this is where we have all of the parameters, the charge, the velocity, the radial distance. And that finishes off this part right here, part B. So we have the electric force and the magnetic force. Let's write them side by side now. Okay, let's use E squared over R squared. There we go. So there's our answer for part B. Now part C was to take the ratio. So let you guys do part C. So what did I say again? Magnetic over electric. So take the ratio of the magnetic force to the electric force. I'll just let you guys do this one solo. So just kind of work it out there by hand. I'll give you a couple minutes on that. Anybody unclear about what's being asked here? So magnetic force on top, electric force on bottom. Take that ratio. And so I'll give you guys about 2 minutes on that. Let me know if there's a question. I'll go ahead and type the question out in the chat as well. Go ahead and give your answers in the chat too once you've got your answers so others can check theirs against yours. And I will say one more, one helpful thing, and actually it's kind of important, is to replace K with 1 over 4 pi epsilon naught. So go ahead and do that as well, because that actually gives a much more interesting result when you put the 4 pi epsilon naught in there. So it looks like you guys, yeah, Tian, you have a good answer there, but substitute in now. Right. Yeah, Sarah, good. There's definitely a V squared in there, but it's not just V squared. Right. Oh, okay, I get what you were trying to say there. Okay, I give a little bit more, maybe a couple people want to finish it off, so give maybe like 30 more seconds and then I'll go ahead and go through it. Good. See if I can clean that up. Okay, so I'm going to go ahead and go through it now. So for the magnetic part, mu 0 over 4 pi, we have E squared, V squared over R squared. We're going to divide by the electric force, so I'll multiply and I'll flip the fraction upside down. So 4 pi epsilon naught R squared over E squared. Okay, so this is coming from 1 over FE here, is this piece right here. So now you can see we have some cancellations here with like our 4 pi's and stuff too. So E squareds will cancel, R squareds will cancel, R squareds will cancel. And what we're left with is mu 0, epsilon 0, and then a V squared. And give me 1 second, actually, I need to bring this down. I forgot to do that before we started. So what we have here is actually something pretty special, but it's not exactly recognizable yet. So let me tell a quick little story. Historically, Maxwell was playing around with the different equations of E and M and thinking about electricity and magnetism and all the experimental work that was done at his time, and realized there was like a mistake in one of the equations. I won't talk about the mistake now, but it has to do with Ampere's law, which is coming later in the lecture. And then probably in a subsequent chapter, we'll talk exactly about why it doesn't hold in general. But essentially what Maxwell did was he worked on the equations and figured out how to correct Ampere's law. And once he corrected Ampere's law, he was able to play around with the four equations to write down a wave equation. So Maxwell's equations imply a wave equation. And in that wave equation, this term mu 0 over epsilon naught pops up. And people understood at that time, and Maxwell understood at that time, that meant that there was a velocity that was equal to, and let me actually, let's just go ahead and spill the beans on it. That velocity happened to be the speed of light squared. So the speed of light was something which was also well known in Maxwell's time. So once he saw this mu 0 epsilon 0 product, he was able to crunch the numbers on that. And he, of course, knew the speed of light at that time. And so he recognized that as the speed of light. So that was one of the big moments, one of the big discoveries that Maxwell made was there was a wave equation that he was able to come up with involving the electric field and the magnetic field. And in that equation, there was this velocity given by the product of mu 0 and epsilon 0. And it happened to be coincidentally, nowadays, not really coincidentally, it has to be that. But in his time, it was like a coincidence. And that was the speed of light squared. So it's a very like big eureka type moment there for the history of physics there. So, so ultimately what we end up for this ratio then to just finish off the problem here is v squared over c squared. Okay. Now there's kind of actually another big problem with E&M, and maybe some of you are starting to realize it at this point. I would hope anyways. It's not particularly obvious, but it's something that's really kind of focused on in the first semester of physics. And that is that equations of motion for different objects don't depend on velocity. So let's write that down. So equations of motion for objects. Remember, one of the big ones was like the motion of an object doesn't depend on its mass, right? And then another one was that velocities are relative, right? And we have to define an inertial reference frame from which we measure the motion of objects, right? And so if the objects depend on velocity, then that's going to break that rule of being able to have all the equations the same in every inertial reference frame. So equations of motion for objects shouldn't depend on their velocity. And so the fact that there's a velocity inside the wave equation given by this mu 0 epsilon 0 product, that was actually also a big problem in Maxwell's time, explaining why that's the case. But that problem was rectified by Lorentz, Minkowski, and Einstein, who basically spelled out the rules for special relativity, which is something you guys will discuss in your next semester. So we'll leave it at that. A little aside there. Okay, so any questions up to that point? Up to this point here? I see there's a chat here. Okay, yeah, Alberto, good. By the way, Alberto, I got your email and I took care of that for you. Okay, so if there's no questions, then we will go ahead and take a look at some stuff with Biot-Savart. So we weren't able to cover Biot-Savart last time. So we're actually going to do 2 examples today of Biot-Savart law. So let's go ahead and write that down. So the Biot-Savart law, it's also just historically, from a historical standpoint, again, it's an empirical equation. But it is something that you can go and figure out once you have Maxwell's equations. So again, it's exactly like the magnetic field of a moving point charge. At first, historically, it's an empirical result, and then later, maybe 100 years later, then Maxwell's equations are fully fleshed out. Then you can solve for that rule from Maxwell's equations. But just empirically, the Biot-Savart law, and this is one that really kind of trips people up because of the cross product. Again, everything with magnetism always has a cross product, right? So you really want to try and get comfortable with that. The Biot-Savart law, again, has this constant mu0 over 4 pi. And then it has, and we'll get a picture for this again, and then it has a current which flows along a direction, so along some path, which is parameterized by L, right? And so this is kind of what we called, maybe similar to what we called dr when we were looking at electricity. But you're going to see dl floating around a lot in these chapters on magnetism. So I'm just going to follow the book on this one and just use dl. But we've seen it before as dr. And then that element there, that I times dl, is crossed into, again, a radial vector, unit vector, r hat, to get the corrected direction. And then always this behavior of 1 over r squared here for any kind of point charge-like system. So since it's an infinitesimal element of current, it's going to be over r squared. We'll see shortly if we have, again, an infinite wire, it'll be behavior like 1 over r, kind of the same that we saw from electrostatics. If we had an infinitely long line charge, we ended up with something like 2 lambda times Coulomb's constant over r, something like that. I'll remind you of that result when we get there. Okay, so this is the Biot-Savart law. Again, it's like an empirical thing. There's no way to really derive the equation. And of course, we could take an integral on both sides, right? And if we select appropriate boundaries, we'll get the magnetic field at some point that we're interested in. Now, notice that this integral expression, this is not like a closed integral. It doesn't have to be closed, but sometimes it does have to be a closed path. Like, for example, if you have a loop of current, if the current is going around in a circle, then it would be closed. But the general picture here for this equation can get a little bit complicated, and the book has some nice figures for that. So do take a look at that in the book. I believe it was in chapter 27 actually is when they have the pictures for that. So let me go ahead and draw just a nice simple picture here. So we'll just look at things kind of in 2D. Here we have a charge like so, and it's moving in this direction. Excuse me, we're looking at Biot-Savart now. So we have a current element, not a point charge. And so here's our current element, and the current in that element is the current I. And this current, this could be a current element of some kind of crazy looking pipe that we don't really know necessarily exactly what it's doing. We may not even be able to parameterize it properly. But if this is the current element there, then the element dl would be tangent to that current element there. So I'm trying to draw it so it stands out a little bit there. So make it a little bold. That's our DL. And DL over here would look something like this. It's just measured along that direction. And we're interested in the magnetic field at some point P over here, okay? And so what is the vector R? The vector R simply points from DL to that point P. We're going to do it as a dotted line here. So that is the vector R there. And then of course there is the radial unit vector there as well, R hat. And that's pretty much all the pieces there that you need for Biot-Savart. But I think you guys can see it's kind of complicated because, again, it describes the magnetic field due to some arbitrary, motion of a current along some arbitrary path. And so, again, we'll want to somehow use symmetry to simplify that expression down. And that is what, by the way, so the direction. Almost forgot about the direction. How do we get the direction? Always right-hand rule, okay? So if we want the direction of the magnetic field there, we take our right hand and we stick it in the direction of the current, the thumb in the direction of the current there, and I have to contort my arm a little bit. So hopefully you guys can see this. So my thumb points to the right and my fingers curl out of the board up there. So the amount of magnetic field due to that current element, its direction is coming out of the board. You need to turn your hand more. Yeah, more. You have to actually like really contort your hand the way you're doing it. It's probably better to do it to like turn your chair or something. So the best way to do it is stick your thumb in the direction of I, and your fingertips will curl out of the board at the point P. So if you're doing it the way you're doing it, so you're doing it like this, but you need I cross R hat. So you actually need to turn your hand this way. So turn your hand this way.
I think.
Okay. So use the right hand rule there to get the direction. Now that doesn't guarantee that that is the direction of the magnetic field at that point. Okay, that's critical. It's critical that you understand this next point. That is the direction of just the contribution to the magnetic field, dB. You have to integrate over all of this wire here, which carries the current. And because you have to do that integral, this wire could be doing some loops all over space, right? And the direction of that magnetic field may not be coming out of the board. For example, if the wire were to kind of curve back, kind of come up over here and then like curve back and come back this way or something, then perhaps the magnetic field would switch directions on you, due to some factors. Actually, probably a better way, actually for sure, if something like this were to happen, then you can see that those contributions along that portion would be into the board. And so that may cancel out this dB, which is coming out of the board. So you have to be really careful. You can use the right hand rule to get the direction of dB, but not B, only dB. So let me type that out for you guys. So right hand rule gives direction of dB, and maybe we can make that bold. Not B. Okay, very important. So it's just the direction of dB. You got to sum up all the contributions for dB to get the full magnetic field. So This is where it kind of gets a little bit complicated. But we're going to look at simple cases because Biot-Savart is complicated. We don't want to be throwing integrals around and doing all kinds of complex math. We want to just get to the physics of it. We want to just focus on something that has some symmetry where the integration can kind of simplify out. We can learn a little bit about the physics, right? So I see there's a chat here. Down. I'm not sure what that was referencing. Maybe you said that when I was trying to do the right hand rule with you.
When you were talking about DP, so I was, I guess the direction is down. I was wondering if the direction is down according to.
Out of the page. So DB is coming out of the page.
Okay.
So my fingertips are coming out. My thumb is in the direction of the current. So it's coming out at us.
Okay.
That's why it's the dot.
Is DL on XY plane, not Z? Is DL not going into the page or?
DL is along this axis here to the right.
Oh, okay.
Yeah, I can maybe that helps clarify. So this would be like the x-axis. This would be the y-axis, right? And so DB is coming out at us in the positive z-axis. So if I were to draw it three-dimensionally, it would look like this, right? So this would be z, and B would be along this direction like this, along the z. I know that's kind of hard to see, but
okay. I totally assumed earlier that DL was going into the screen. So.
I see. Yeah, you have to go to where the current is. So this right here is our current element right here, if I bring it over here. So the black arrow there was meant to be DL. So that's going in the positive x. And then R hat is pointing from the current element to the point that you're interested in knowing the magnetic field at. Does that make sense? Does that make sense, or it's unclear?
Yes, it makes sense.
Okay.
Mute myself earlier, sorry.
Okay. All right, so let's go ahead and do an example of Biot-Savart. We'll go ahead and do it for a straight wire that has a just a current I flowing through it, and we'll look at a finite length of wire, but we'll be ready to take the limit. I'll probably make you guys do this. We'll be ready to take the limit as A goes to infinity. Okay, so that way we can look at an infinite wire. All right, so let's go ahead and get right on that then. I'm going to actually copy the diagram from the textbook here. So 1 second, I'll have that ready. There it is. So we have a nice little figure to go by here. Save some time drawing. I know you guys want a little bit of time to copy that down, so I'll give you guys some time to copy that down. So go ahead and do that now. It looks like Greg has decided that he's had enough, but I think he enjoyed it. He said, I had fun there. Good night, Alaric. And he did actually stay past 50 minutes, so maybe he was a bit interested there at the end. Okay, so are we ready? Ready to get into this one? So just to have a problem statement here, we want to calculate, let's take the bold off, calculate the magnetic field at the point P due to the long straight wire length equals 2a. We'll take the limit as a goes to infinity in a second. Okay, so how do we even start on this problem? Well, the first thing you got to do is write down the Biot-Savart law, right? You see a problem like this, calculate the magnetic field. You got to be thinking Biot-Savart. Okay, that's step number one. Biot-Savart. We just saw the Biot-Savart law on the board. We just saw it, right? It was just, don't look in your notes. Don't look in your notes. We just saw it. Let's try to recall it from memory, okay? Let's try to recall it from memory. So the Biot-Savart law says dB is equal to, okay, there's a constant, right? What's the constant? What's the constant part out front? It keeps showing up, this mu and the pi, right? What's the constant out in front? Say it in the chat. Don't look at your notes though, be honest. David says mu 0 over 4 pi. Don't look in your notes. Is that correct? Do we agree with that? Mu 0 over 4 pi?
I agree.
We agree with that? Okay, yeah, let's write that down. So mu 0 over 4 pi. All right, then I kind of remember, it's kind of like electricity, right? Like Coulomb's law. What do we divide by? It's like Newton's law of gravity, Coulomb's law. What are we supposed to divide this by?
R squared.
R squared, but are we looking at our notes? I hope not. Okay, does everybody remember? It's like 1 over R squared. What's next? What's next? Biot-Savart. Maybe we can look at the picture and get a little bit of a hint here. I look at the picture, I see, oh, there's a current. There's a current, I. Where does the current go? Does it go in the denominator? Does it go in the numerator? Does it go
I think
in
it's I R hat.
I R hat? Not quite. Close though, very close. I like that. I like that guess there. There is an R hat in here. There's an R hat over here. There's a cross product between something and R hat, right? All these magnetic field equations, they always have this cross product in there. So what's the other thing? Well, I'm looking at this diagram over here. I see a DL. Where does DL go? Does DL go into this thing? Is there a DL here?
Yes.
Is it DL right here?
Yeah, I was about to say that.
Like this? Yeah? Okay, good. So yeah, I agree. So DL right here. DL vector cross R hat vector. Okay, so that's how you remember things. You got to like keep trying to remember them. Okay, and maybe take some hints from the picture, that kind of thing. So this is Biot-Savart. So calculate the magnetic field at the point P due to the long straight wire of length 2a. Now, what do we do from here? Well, we have to kind of start identifying things, right? We know we're going to have to do an integral. B is going to be some integral of this thing. Mu 0 I over 4 pi. These are all constants, right? All of these are constants. DL vector cross R hat over R squared. Okay. Everything on the outside is constant. The current's constant, mu 0, 4 pi, those are all constant. Now, how do we handle this business with the cross product here? Well, what I'm thinking is maybe we do the magnitude, take the magnitude of this thing, and then just get the direction at the end with the right-hand rule. What do you guys think about that? Does that make sense? Let's take the magnitude of this thing and just get the direction later. In fact, we can get the direction right now, actually. What's the direction of dB? Well, right-hand rule. So if I take my thumb and I stick it in the direction of the current, my fingers will curl in the direction of the magnetic field. Thumb in the direction of the current, fingertips tell you the direction of B. So for me, it's into the board, into the screen, right? Into, so it's towards my monitor. That's why they have an X in the diagram. Excuse me. There's an X right here. Magnetic field is going in. Here it is, boom. It's going in. Now, is there a component of the magnetic field that goes in any other direction? Well, the current is always up, right? The current is always up here. So as long as we're on that x-axis, as long as we're on the right side of this wire, the magnetic field will always be into the page. On the other side of the wire, you could wrap your fingers around and you could see on the left side, this is my left side now, magnetic field is coming out of the screen. So the magnetic field really is circulating around this wire here. The magnetic field is circulating. It's a circular, it's a cylindrically symmetric situation, right? So the magnetic field is circulating around this wire. Okay, so the direction is taken care of. At that point on the x-axis, actually anywhere on the x-axis, on the positive x-axis, the direction is going to be minus z hat. Why minus? Because into the board here for this coordinate system would be minus z. So let's go ahead and take the magnitude of this and we'll just put minus z hat. Okay, I see a lot of chats here. Okay, so yeah, good. A lot of people were saying like r squared, sometimes d on top, I, dl, cross r hat, good. Sounds pog. I always forgot what pog stands for. Right, round, like a record. Okay. Okay, so here we go. We've got the direction. Minus z hat, that is a constant vector. Get that thing out of the integral right away to avoid as much confusion as possible. Bring that sucker outside the integral. And then we write the magnitude dl cross r hat is simply dl times the sine of the angle between the dl vector and the r hat vector, which actually in this diagram they've called phi. Right? They've called it phi here. And in the interest of, saving a little bit of time here, we can kind of jump a couple steps here. So sine phi, what is sine phi going to be? Well, sine phi is, this, so let's go ahead and maybe recall that. Yeah, so maybe we want to do, probably we could say cosine, how do I want to write this? Well, let's just leave it as is for now. Let's not try to do too many steps all at once. Basically what we have is mu 0 I over 4 pi, and then we have a minus sign, and we have a z hat vector, and we have an integral of magnitude dl sine phi over r squared. I think we all know what r is here, right? R is, it's in the diagram, so it's like side squared plus side squared, right? X squared plus y squared, take a square root. So that piece we know. dl, what is dl? Well, L runs along the y direction here. So where's my mouse at? dl runs in this direction from minus a up to plus a, right? So we know that dl is going to be essentially dy, and it's going to run from minus a to a. And so what we can do now is we keep all the stuff out in front first. So minus mu 0 I 4 pi z hat, and then integral from minus a to a. And then we want to plug in dy for dl, and then sine phi we're going to write as there's no, I don't think there's a really great way of showing this, but let's just go ahead and plop it in here, right? The sine of this angle here is going to be the same as the sine of this angle here. But I really dislike how it's been drawn here in the diagram, because it just gives you the impression here that this angle phi, yeah, I don't know what to say about it, but basically, like, let's say this is a theta here, and sine theta is the same as sine phi. And the reason is because of the quadrants, right? So sine phi is going to be equal to sine theta here. The phi is in the second quadrant, and sine is positive in the second quadrant, and it's positive in the first quadrant. And if you shift the sign by 90 degrees, or excuse me, if you shift the sign by 180 degrees, then you end up with minus the sign, right? And then from there, we don't care about the direction, so we ditch the minus. I don't know. It just seems like it's not a very clear. It's not very clear from this angle here that it's going to be the same as the sine of this angle here. But if we were to, let's see. So we have a vector dl here, and we have the vector r hat here. Okay, the cross product makes it clear that it's this angle here that needs to be the sine. It needs to be sine of phi here. But property of the cross product. Now this is probably the best way to see it right here. So I don't know, maybe it's just me and I just don't see like a clear argument here, but okay, this one I know works for sure. So if you have A cross B, that is the same as minus B cross A. Okay, so if I make minus r hat is in this direction, that is the angle theta. So minus r hat. That's the angle theta there. That's the angle theta, because phi plus theta has to be equal to 180 degrees, because they're constrained to this triangle right here with this right angle. So phi, this has to be 180. So theta plus this angle has to be 90. And so this is the angle theta right here. So if you do minus r hat cross dl, then it's clear that it would include sine theta. So I think that's a little bit of a weird way for them to draw the diagram here without being explicit, that you want to take the sine of this angle theta right here that I've drawn. I don't know. You guys let me know if it's not clear, if it's clear to you guys, or if you have a better argument as to why sine of phi should be y over r. But I think this proves it outright right here. So I think that's plenty good for a proof, just using this anti-symmetry property of a cross product. And so basically the reason we just went through all that is because we need to know what that sine of phi is. Now we've shown it that sine of phi is the same as sine of theta, which is y divided by r. So that's where we had to get to. So you guys let me know if that's unclear. So copying things down again, minus mu 0 I over 4 pi, z hat vector, integral of dy from minus a to a times, we have an r squared in the denominator, and we have an r from the sine theta. So it's going to be y over x squared plus y squared to the power 3 halves, like so. Okay, And this integral is not so bad to do. Okay, this is just a simple u sub integral. You set u equal to x squared plus y squared, and you calculate dy, and you get like, 2y dy, right? So this is a simple u sub. We're going to skip over this one. That's just math. Let's get to the physics here. What we end up here for our answer is, and I'll factor the minus sign out. So mu 0 I over 4 pi times 2a over x square root of x squared plus a squared. And then this is going to be in the minus z hat direction. Just factor that all the way out. So as a vector, b is this from Biot-Savart. And I hope you guys noticed that that actually wasn't that bad to go through. But maybe it was just me, like I don't see it. I don't see a clear argument there geometrically. But from the cross product, I think that makes a little bit more sense. So we had maybe like this little hiccup right here with the sine phi. Once you figure out what the sine phi is, I think it's straightforward just doing this integral here. This is a simple u substitution. U equals x squared plus y squared. Du is 2y dy, and I'll let you take it from there. Okay, so I showed the magnetic field is this value, a distance x away from the wire, at the midpoint of the wire. Now I want you guys to do something for me, and I'll actually put you guys into break rooms for this. I want you to calculate the following thing. Limit as a goes to infinity of b. So what does this equal? Okay, and we are going to do breakout rooms here. They are now open. Go ahead and join the room. We'll go ahead and take maybe 10 minutes tops on this. It should maybe only take 5. Okay, just letting you guys know that you're the only group with 2. So do you both understand what's being asked?
Yeah, we're just setting a to infinity and just see what value comes out.
Setting a to infinity, okay?
Yeah, as a goes to infinity, so
You want to take a limit and you want to do it carefully, right?
yeah.
Okay. Tatiana, you understand?
Yeah.
Okay. So since the two of you kind of get it, just work with each other, figure that out. Go to the next room. Okay, how are we doing over here? Do we all understand the question?
Yes. Or at least I think I do.
Okay, and then when the phone says yes, Elaine, you say yes. Okay, I'll just checking on that, and then I'll go to the next group then. Hello? Do we understand the question?
Yeah, we solved it kind of.
You
I think
solved it?
I think, is it 1?
As okay, kind of,
Is
as
it
A
1?
approaches infinity, B approaches infinity over infinity, right?
Yes.
Which is 1.
Remember that we're taking a limit here. We're not like plugging in a value of A or anything like that, right? This requires precision. This requires mathematical precision, right? We can't just throw infinity into the equation and cancel out infinities or anything like that, right? So that's an indeterminate form. You have to figure out some way to
L'Hopital,
mitigate that.
right? L'Hopital rule. Will I have to use that?
L'Hopital's rule certainly applies. However, if you use L'Hopital's rule, you may run into some kind of issue. Okay. Anyone else have any input?
Oh, we thought it was going to be one.
Definitely not going to be one. That wouldn't make any sense, right? Because if the wire becomes infinitely long, presumably you would have like more magnetic field there, right? Because we're a finite distance away from the wire. We're not infinitely far away from the wire, right? So it's not going to be like 0, for example. It's certainly not going to be 1, because that would imply that the magnetic field is constant everywhere, because there would be no dependence on space, right? So it can't be some fixed number. It's going to have to depend on how far you are away from the wire. If you're further away from the wire, you would expect it to be less. If you're closer to the wire, you'd expect it to be more. So carefully develop a process for taking that limit, okay? I'm going to go to the next group.
Hello, Professor.
Hello, how are we doing?
Hello.
Question?
So we're getting my idea is that A is probably a lot bigger than X or X squared. So we can kind of just say that those factors can kind of just go away. I don't know the actual property of it. It's come calculus thing. So I'm getting like 2 times infinity over infinity, the square root of infinity squared, which is it's basically I'm getting infinity over infinity.
You never plug in infinity.
Yes, Professor. So we get 2.
No, you don't get 2.
Oh.
You're plugging in infinity if you get 2.
Are we taking, we're taking A to infinity, right?
Yes.
Okay.
You need to be careful. You need to manipulate the thing that you're taking the limit on. There's one thing in the numerator and one thing in the denominator that you're taking the limit on. So maybe isolate those.
Is it 0?
If you have an infinite wire and you're a finite distance away from the wire, it's not going to be 0.
Okay. Huh. Then there's no way what they wrote down here is right.
There's no way what?
There's no way what I'm seeing here is right on the chat. Right. Can you see that?
I forgot that the denominator there. It's the one we were looking for is 2a over s squared root. I forgot to include the slash there. That's what we're
Okay.
looking for.
There we go.
So what you need to do is you need to be careful. You need to develop a procedure here for taking the limit on this function of A, right? And so one group pointed out, oh, it's infinity over infinity. We can use L'Hopital's rule. Well, yeah, you can use L'Hopital's rule, and eventually it will work. But there's a much easier way to get to the answer. So I'll let you think about that since this is my first round through.
All right, thank you, Professor.
Okay, how are we doing over here?
I got it to be equal to 1.
Yeah, you can't plug infinity in.
Yeah. Wait, what do you mean?
If you're getting a constant like that, you can't be plugging in infinity. It sounds like plugging in infinity and like canceling out infinities or something.
No, not really.
So what did you do? Walk me through what you did.
So the whole formula, what was it? Oh wait, I have the screenshot right here. Where is it? So since we're only dealing with A's, so I just move that mu0 I 4 pi and 2 over x to like just on their own, and then I just take the limit of a over square root of x squared plus a square.
Mm-hmm.
And since x it's fixed, so I just treat it as like a constant.
Mm-hmm.
So then and then a constant to as a goes to infinity is kind of irrelevant.
Mm-hmm.
So then it would just be a over square root of a square, and then that would just simplify to a over a,
Yeah.
and then I got one from that.
Yeah, but what's the answer though?
Oh
I'm not
yeah,
asking you for the
oh
limit of that function.
yeah. The rest of the function would be that is it mu that is mu0 I times 2 over 4 pi x.
Yeah.
Yeah, that's the answer.
Cancel the 2 and the 4.
Oh yeah, cancel the 2 and the 4. That would just be mu0 I 2 pi would be equal to b.
No. Mu0 I over 2 pi x.
Oh yeah, I forgot the x.
Yeah, Tatiana, how are you doing?
Hi, I'm doing okay. He got it before I did.
So you didn't really follow that, or?
I did more or less, but I'm on the phone, so I kind of squiggle.
Okay. Yeah, so I'll go check on the next group then, and I'll probably close the rooms after I go through this one time. I really want to make sure that we have time to get through everything this time. Just really ended early last time, or we didn't cover everything, I mean. Hello? How are we doing over here? Good. Elaine? Sarah? Munfeng, what answer do you have? Okay, so good and good. So what's your guys' answer so far? Okay. Elaine, I haven't heard from you yet. Ah, okay. Eating. We can take a break soon. It's been almost, I took a break at about an hour and a half with the last class. I think it's right around the time maybe we could take a break soon. Have you had a chance to work on it at all yet, or you've just been kind of eating? This is one we've got to, it's one of those questions where it's important that we understand how to get the limiting behavior on some of this stuff. So there's not a whole lot of physics in this question, other than we often make this kind of approximation that, a wire is infinitely long. So we get kind of like an approximate answer. Okay, anyways, I'm gonna go to the next room. I am gonna close the rooms fairly shortly. Just letting you know. Hello?
Hello.
Hi, Professor.
How are we doing over here?
Doing fine. I'm still kind of, Lucas, it's not your turn to talk.
I can't hear you. Your voice kind of like went super low.
Oh, could you hear me now? Sorry.
It's okay, yeah.
No, Lucas.
No, it's fine. But maybe you should, maybe it's not possible, but maybe you can send him to another room or something so you can focus. But Lick, Alberto, how are you guys doing?
Because in the restroom.
Okay.
I was wondering if it was be like when you do just the limit part, would that be equal to something like 2 over x, or just 2. And when you put it together with the rest of the problem, like I was thinking it was like mu naught I over 2 pi x.
I think you're so you are on the right track there, but you seem unsure of the process that you used to get there. So maybe you want to let me know the process that you used to get there, and I can judge better.
Well, I was thinking that it was something like the a's go to infinity, therefore that part of the problem, it becomes infinity over infinity becoming 1. So 1 times 2, and then 1 times
No.
x.
No. Infinity over infinity is not 1.
It indeterminate. It's
Yeah, indeterminate form.
Um.
So Alberto, what you need to do is since you've gotten an expression, or you're going to get an expression, which is something like infinity divided by infinity, that's called an indeterminate form. What it means is you need to figure out how to manipulate the equation to get rid of the infinity over infinity. So maybe there's some way you can factor the bottom
I'll do it.
and cancel out an a on the top or something like that.
Okay.
Yuen, is that what you were suggesting? You know how to do that one?
Now I use L'Hopital and I did run into. I'm not sure what. I arrived at 2 pi over 2a to the 1 over square root of 2a, which
Over square root of 2a. Can you go through that one more time?
is 2 pi over 2 pi x over square root of 2a. So that will make it.
Where's the because you use L'Hopital's, right?
Yes.
There can't be an a in the final expression because you're
Okay.
taking the limit as a goes to infinity, right?
True.
So try to factor the bottom. Factor an a squared out of the bottom term outside the square root, and it becomes a, right? If you pull a squared out of the square root, it becomes a.
That is true.
All right, Lick, what do you have? Did you make some progress before you left?
I'm still doing it right now.
Uh-huh.
So yeah, haven't had much progress yet.
So try what I just said, factor an a squared out of the bottom so you can
Okay.
cancel the a on top. So that's kind of the idea here.
Okay.
But I am going to close the rooms here in a second after I check up on room 1. And I'll go through the process kind of quickly. All right.
Okay.
See you guys later.
Well, it is what it is.
Oh, welcome back, Professor.
Hello.
We figured it out.
Figured it out?
Sergio, you go.
We'll
No, I didn't figure it out though.
No, you did. You totally did.
You
that.
literally figured it out.
Stop lying. Whatever. We figure out it's 1 over x.
You pulled an a square out
Yes.
and it canceled with the a on top.
Yes.
And you were left with mu 0 I over 2 pi r or x.
Yeah.
Okay, so you have the right answer then. All right, I'm going to close the breakout rooms now. So I'll see you guys in like a minute or so. What we're about to do is factor an a squared out of the denominator of this expression here. When we factor out an a squared from the denominator, it comes out of the square root as an a, and the x squared term is divided by a squared, and then we have a plus 1 here, and then the two a's can cancel. So when you take the limit as a goes to infinity, the term x squared divided by a squared simply goes to 0, and you're left with mu 0 I over 2 pi times x. Okay, so people are joining now, so maybe yeah, I'll close the rooms now. Everybody can come in here. We'll take a break soon, by the way. We've been going for about an hour and 34 minutes, so it's probably a good time to take a break right after we cover this question here, and then we'll pick back up where we left off. Waiting on a couple students here, 3 students. Anybody have any questions while we wait? Got a chat here. How was your day?
Okay.
Yeah, it's okay. I'm pretty tired actually. I didn't sleep well last night. And actually just recently, my tooth, like half my tooth fell out. I've been having some tooth pains recently, like the last couple weeks, and I think it's from like getting some like seeds in between my tooth, like my teeth back here. And like it's been kind of painful when I bite down on the tooth. And then I think one time I kind of really like bit down on it kind of hard and it hurt. And maybe it cracked then and it just kind of stayed in, because the other night it kind of like fell out. It was really weird. It didn't hurt or anything. It's just really weird to just have like an adult tooth just kind of like fall. Yeah. To go to the dentist maybe Wednesday, I think, tomorrow. Go to the dentist. It wasn't bloody or anything. I think that what happened was it actually cracked like a couple weeks ago, and it was just kind of just in that position, because it was really painful like a week or so ago. And then yeah, I don't think I'll be having any candy on Halloween anyways. Though when I was a kid though, I used to go out with this massive pillowcase, like a body pillowcase, and like fill the whole thing up. It was like 10 pounds of candy or something like that. And I'd go from like 6 p.m. until 10 p.m. That was kind of fun. Anyways, all right, everybody's here now. Yeah, it's all about maximizing the gains. And then you just eat all the candy like super fast. But now I don't do stuff like that. If I have candy, like, yeah, it's like every once in a while. I didn't go to a rich neighborhood, but I just had a large area around me that I would just go literally like algorithmically through like all the houses in every neighboring neighborhood. But yeah. Okay, let's go ahead and yeah, I don't recommend you guys have a lot of candy either. You know, one of the things you can do to actually do better in my class is reduce your added sugar intake and reduce the amount of saturated fats in your diet, okay? Scientifically proven to improve your overall health and brain function. All right, anyways. Let's get back to the question at hand here. So we want to take a limit on this function here, and I've kind of already written out what we need to do. So let me go ahead and back it up here. What we want to do is we want to factor a squared from the denominator. We can cancel the 4 and the 2 up top. Like so, and we go ahead and we pull out an a squared. So if I divide through by a squared, I better also multiply by a squared. And then use the property of exponents, or square root is the same as an exponent, right? To bring the squared piece outside of the integral, okay? And that's going to come out as an a. Now, really, it should come out as magnitude of a, but a is a positive number, so we don't have to worry about that. It's simply a, so we get rid of the absolute value signs here. But yeah, once we do that, this term here becomes 1, and we're able to cancel the a in the numerator with the a that we pull out. And this term right here, x squared over a squared, this term tends to 0 in the limit as a goes to infinity. So what we're left with is 1 divided by the square root of 0 plus 1 times 1, right? So all these a's are canceling to 1s here, and then this one right here, x squared over a squared, goes to 0. And this is the answer that you get right here. Or rather, this answer right here. So mu 0I over 2 pi x. Okay, mu 0I over 2 pi x. Questions about that? I know a lot of you were able to get that, but I think a couple of you were still working when I closed the rooms. Give me a thumbs up if that made sense. Even if you didn't get that answer, does that make sense? Because obviously we have the recording here, so you can watch it again or something maybe. Or if there's a particular question there, let me know. Okay, so the magnetic field then of an infinite wire is going to be mu 0I over 2 pi x. And a lot of times we'll just replace x with r. And r is the radial distance that you are away from the wire. Remember, a wire has cylindrical symmetry. So a distance r away from that wire is the same in any angular direction. Or excuse me, it's the same no matter what the radial direction is. You know, if you want to rotate an angle theta, it's the same. Okay, so that would be a good, let me leave that there. That would be a good place maybe to take a like a short break. I do have an example, so maybe we should combine our break with an example. I think that's what we will do here, and I'll maybe do a 15 minutes break. So a long straight conductor carries a 2.5 amp current. At what distance from the axis of the conductor does the resulting magnetic field have magnitude B equals 0.5 times 10 to the minus 4 Tesla? So about the magnetic field of Earth there. Oops, Tesla. No picture for this one. If you really want to get a picture going, it looks like this. And there's some magnetic field circulating around this thing. Magnetic field really is circulating around this wire, by the way. This is not like this is an actual depiction of what the magnetic field is doing. It is circulating around the wire. And we want to know how far away, right? At what distance? And does the resulting magnetic field have a magnitude of half a Gauss, right? 10 to the minus 4 Teslas is 1 Gauss. So this is half a Gauss, or this is, 50 times 10 to the minus 5 Tesla, which is about the magnetic field of the Earth. Okay, so we'll combine break plus this problem. I'll give it 15 minutes. We'll meet back here at 8:08. Let's make it 8:09 just to account for the time that we have now. So meet back at 8:09. Feel free to chat or whatever. Somebody asked what people were going to dress up as for Halloween. Whatever you guys want to do for your break, okay? I'll be back at that time to go over the question. All right, see you guys soon. Alrighty, we're back. Okay, see some chats here. Yeah, 1 centimeter comes out exactly to 1 centimeter here. Let's see how that happens. Yeah, let's not talk about swallowing money, okay? You just keep the money away from him. That's how you prevent it from happening. Okay, so a long straight conductor carries a current 2.5 amps. What distance from the axis of the conductor does the resulting magnetic field have magnitude half a Gauss? Well, we start with the fact that the magnetic field is mu 0 I over 2 pi r, and then we solve for r. So r equals mu 0 I over 2 pi b. Plug in your numbers. I didn't tell you guys this, but I think you already have experience with it. Mu 0 is equal to 4 pi times 10 to the minus 7 Tesla meter per amp, I believe are the units there. Now, recently, fairly recently, within the last couple of years, I believe in 2018, there was a redefinition of the electric charge, the fundamental charge, the charge of the proton E. There was a redefinition of that charge, and by redefining the charge E, the accepted numerical value of mu 0 has changed. It is no longer exactly 4 pi, but it deviates slightly from 4 pi around the third decimal place or something. So 4 pi is, roughly like 12 point something, right? So now it's like 12 point something something, and then slightly different than 4 pi at the third decimal place. You can read about it in your book. But yeah, so you will just be using 4 pi times 10 to the minus 4 in this class. No reason to change. Again, the amount of error there that might be introduced is extremely small. Why did it take till 2018 for them to fix that? It's not about fixing it. It's about changing the definition of something because of a new way of measuring something else, right? So usually what ends up happening is a lot of our units are based on, how do I say it? Based on like a standard measurement of something, like the kilogram, right? There's some mass in France in some, secure location somewhere that is defined to be 1 kilogram, right? So when very precise techniques for measuring something are developed, then sometimes there can be a redefinition of units. Excuse me. Okay, so what we end up with is exactly 1 centimeter here. We have 4 pi times 10 to the minus 7. The current is 2.5, and we have a 2 pi in the denominator, and a b is 0.5 times 10 to the minus 4. If you work out the numbers on this, you get exactly 0.01 meters or 1 centimeters. And that answer should have 1 sig fig, because we only gave the magnetic field as half a Tesla, but if you work the numbers out on the calculator, it'll tell you that's exact. Okay, I doubt there are any questions on this one because it's so straightforward, but are there any questions on this one? Okay, there are no questions, so we will go to the next example. And here it is. And I will just get you guys started on it right away. two long straight parallel wires perpendicular to the xy plane, each carrying a current I but in opposite directions. Let's go ahead and drag this out here. Two long straight parallel wires perpendicular to the xy plane, each carrying a current I but in opposite directions. Let's say the figure shows A, find B at the points P1, P2, and P3, and part B, find an expression for B at a point to the right of wire 2. Okay, it's all, as a matter of fact, it's all analytical, not just this part, but okay, this is an analytical problem, so your answers do not have numbers. So basically we have a figure here. We have two current carrying wires being shown here. Wire 1 has a dot indicating that that current is coming out of your screen and towards your face. And we have an X for wire 2, which means that that current is headed into your screen. So the currents are flowing in opposite directions here. Now it wants you to calculate the magnetic field, the total magnetic field at the points P1, P2, and P3. So in order to do that, you have to calculate the magnetic field due to wire 1. You have to get its direction. And then you have to calculate the magnetic field due to wire 2, and you have to get its direction. And you have to add them up as vectors. Remember, we have the principle of superposition when we are doing electricity and magnetism. So not only the electric field, but also the magnetic field obeys the principle of superposition. That's just a consequence of the electric and magnetic fields solving or being the solutions to linear differential equations. That's where the principle of superposition comes from. So we have 3 different points of interest here. So you have to do that 3 times in part A. For part B, find an expression for B at a point to the right of wire 2. So it could even be at the point P3, but you don't want to use the distances that are given for part B. You want to look at an arbitrary point and maybe add a label, like maybe say X, right? So we're a distance X away from wire 2. So how far away from wire 1 are we? Okay, so that's the idea here for this problem. I think I've given you enough time to copy it all down. Maybe not, so I'll give maybe 10 more seconds here, and I'm going to put you guys in rooms again to work on it some more. And we'll go ahead and recreate the rooms, and we'll do 2 people per room on this one. Okay, here we go, opening up the rooms now. Go ahead and join your room. Take no longer than 10 minutes on this one, okay? We don't want to spend too much time on it. Okay, let's jump into the first room. Hello. Do we understand the question here?
Yeah, I was not in the room when the questions was posted.
Okay, so then maybe that's good. I came here first, so I'll let you go ahead and copy it down. There it is.
Oh, okay.
Also, this is example 28.4 in the book. if you want to get the ebook open or something, that's fine. Sarah, you understand what's going on here?
Yeah.
Yeah, okay. And then Yuan, one more comment about it. You're not going to be using any numbers in any of these parts. So notice that the distances here are given in terms of d, and there's no value given for d, right? And there's no value for the currents here.
Okay.
The dot means it's coming out of the screen.
Yeah.
And the X means it's going into the screen. Okay. All right, I'll come back. Hello.
So
Understand the question over here?
yeah, we're just starting on it.
Okay.
Nope.
As long as we understand what's going on, then I can just come back later. So we're good?
Yeah.
Alex?
Yeah.
Okay. Hello? Do we understand the question? And are there any questions?
Oh, I don't think we have questions right now.
Okay, so we understand the question. I'll
Yeah.
go to the next room. Wenfeng, you're good? Okay, next room.
A magnetic field at a distance from a current carrying wire.
It's not the same as the center of the loop one.
No,
Okay.
that'd be a totally different equation because it has to factor in the current coming from the entire loop.
Hmm.
So do we understand what's going on here in the question?
Yeah, this was like one of the pre-lecture questions, right? Or like one of them.
It might have been. I don't remember assigning it as a pre-lecture question, but this is an example from the book, straight from the book. So, all
Got it.
right. So if there's no questions for me, then I'll just go to the next room.
Sounds good. Thank you, Professor.
Later.
Where's our
Hello.
perpendicular? Wait, I'm confused.
Yeah, Professor,
Professor.
this isn't their, oh, no, they're not perpendicular, they're parallel.
Parallel. Yeah.
Wait, straight parallel wires perpendicular. Oh, sorry. Okay, sorry.
Yeah, perpendicular to the XY plane. I see what you're talking about. Yeah. It just means you're looking at the XY plane, and then the dots and the crosses are kind of coming out at you or going in away from you. So other than that, do we know what's being asked here?
Not really, I'm a little confused. We still use the same formula we used prior, right?
Yep.
It just significantly much more, right?
Yeah, I mean, it's not too bad though, because there's really not much to plug in or calculate. So it's really just about the setup here.
Mm-hmm.
So if you can set it up, get a common denominator and then add the two expressions. I mean, the figure already kind of gives you a little bit of the answer, right? In where it says B2 is up and B1 is down at the point P1. Really, you should use the right-hand rule to figure that out. So put your thumb out of the page and your fingers curl downward at the point P1. So B1 is down. And
I drew a circle around it and then drew like the direction of.
That's a good idea, yeah. That's a really good idea to make sure you understand it's always circulating around. Yeah. Tatiana, any questions?
No, I think I'm following.
Okay. All right. I'll be back. Okay, I'm back. Have you had a chance to get started?
We're
Yeah.
All right. Why don't you tell me where you're at, Sarah?
Because my question is on a different page, I'm kind of redrawing a simpler diagram just to make sense for part A. Just in retrospect, where the wires are, where the 3 points are, and their distances in between.
Okay. So just for point P1.
No, for all three of them, because like I said, I drew the original diagram on a previous page, so I didn't really want to flip back and forth.
Oh, I got you. Yeah. Did you need me to share the diagram for you again?
No, I got it. Thank you.
Okay. Yeah. So the question is all analytical, right? So there's not much to plug in. You just have to plug in the right value for the radial distance, and then you have to get the direction correct. So whether it's the positive y or negative y direction, but it's all kind of spelled out in the figure. But just make sure you get to practice with your right hand rule. And I always see you use the right hand rule with like the 3 fingers. This right hand rule is not as effective as the ones that I'm teaching you. So the ones that I'm teaching you with the thumb and the fingers are a lot more effective at getting the information. And there's less of a struggle of trying to line up your fingers with the vectors. So the general rule is when you have a current and you want to know the magnetic field, stick your thumb in the direction of the current, and your magnetic field will curl around that current according to your right hand, not your left hand. You should do the same thing. Say it again.
Did you say left or right hand?
Right hand. Always right hand, because it's right hand rule. Yeah, and the other ones are like for the cross product and stuff, stick your fingers in the direction of the first vector, curl them in the direction of the second vector, and your thumb points in the direction of the cross product. You should learn all of those right hand rules because they're very useful. It's much easier to know those rules than to just have one thing that you're trying to fit to every case. Because here you have 3 vectors, right? If I put my fingers like this, I have 3 vectors. I have to match 2 vectors, like V and B, to get F. Well, if I just have my hand like this, I only have to match 1 vector, right? And I just curl my fingers towards the other one. And I don't even have to curl my fingers exactly towards the other one. I just have to curl them in the direction of the other one, and I already have the direction of the cross product. So you need to start practicing that because it's very helpful and it's much quicker. There's a couple different rules you have to remember, like where do I stick my thumb, like towards the current or towards the velocity. Where do I stick my fingers, like, okay, towards the velocity, and then curl them towards B and so forth. But once you've learned them like one time, you start to see all the connections, and then it works out a lot easier.
Yeah.
Anyways, any questions about the actual problem here? Good. Okay, I'm going to go to the next room then.
Thank you.
Hello.
Oh,
Hello.
Good.
no, we're
we got stuck.
confused.
Which part?
part
How?
A.
Part A, yeah.
Point 1, P1.
Yeah.
Use the right hand rule to figure out the direction. So the magnetic field due to wire 1 is down, right? So that one's going to have a minus sign. Magnetic field due to wire 2 is up. It's going to be plus.
Oh wait, so are the 2 wires like on top of each other?
No, they're just the point P1 is just a different distance away from those 2 wires.
Oh, okay.
Did you not have a chance to copy down the figure?
No, I have the figure, but I'm just confused on how
We
the
had
wires are
trouble visualizing
located.
it.
Dot and cross notation. Dot means the current is coming out of the board, out of the page.
And then X is in.
X is in, yeah. You need to think 3-dimensionally for these problems, right?
Mm-hmm.
So that's why we use the dot and the cross notation, because if we If we don't, then we have to always draw a 3D diagram, and you can imagine how kind of challenging it's going to be with all this information on the same diagram, and it's three-dimensional, right?
Mm-hmm.
So let me go ahead and just share this real quick. So this current is coming out of the board. So the magnetic field is circulating around this wire in this fashion here. So over here at this point, the magnetic field is down. And over here at this point, the magnetic field is up. So maybe this is like, if this is a wire 1, then this is P1 over here. And this is P2. Oh, well, okay, that's not entirely accurate because it's not symmetrical, but right-hand rule, right? The magnetic field is circulating around like this. And the distance between the wire and the point P1 is R, which in this case, we just read it from the diagram here. It's not 3D, but it's 3D minus D, right? This is the distance 2D there. So this distance right here, 2D. So the magnetic field, or sorry, the magnetic field is mu 0 I over 2 pi r. This is going to be in the minus y hat direction. I want to make it a vector. And r here is going to be 2D. Does that make sense?
Yeah, it makes a lot more sense.
Okay, now do the same for wire 2 and add them like vectors.
Okay.
You guys tell me, before I go, you guys tell me, what's the distance from wire 2 to the point P1?
40.
Wire 2 to P1. Yeah, 40.
Okay, good.
Oh wait, so once we find the magnetic field of both of them, we just like combine them?
Add them as vectors.
Oh, okay.
Yep.
Yeah, that makes sense.
Any other questions?
I don't think so, not yet.
Okay, we'll go to the next one. Hello, how are we doing?
I think we got P1 and P2, the magnetic field at P1 and P2.
Yeah? Are you guys working together on it, or?
Yeah, we are writing in the chat.
Oh, good, okay.
Yeah.
All right, good, so just keep on going. Probably close the rooms maybe in like 2 minutes or so, I'm thinking. I think
Okay.
we spent a decent amount of time on this one.
Okay.
All right, I'll be back later. Hello.
Hello, Professor.
How we doing?
We're doing good.
Okay.
Think we have the correct answer,
Okay.
or at least all 4 of them.
Oh, so you're done with A and B?
We think so.
Yes, we
Okay.
think so.
I'm going to close the room soon. Just go ahead and take another look at it. Maybe you find a mistake or something, or if it's good, just double check. I'll close the rooms in about 1:30.
Okay.
B1 is pushing up. Hello, Professor.
Hey, where are we at on the problem?
I think we're
Well,
getting
the
it. We're
third
trying to
one.
figure out point 3 now.
Okay, good. Yeah. Good. I'm going to close the rooms in about 1:15. Okay, just letting you know.
Okay, thank you.
All right. Any questions, or you guys are good?
I think we got it.
Be okay.
Okay.
Mm-hmm.
Okay. How are we doing over here? Did I scare you? I can't hear you. It's muted. Anyways, I'm just letting you guys know I'm doing my last round now. Sarah, what's your status?
I think I got pretty much most of part A, but I'm double checking one more time, and I've been muted most of the time because my family's noisy right now.
It seems like the two of you are having the same issue.
Yeah.
So yeah, Nguyen, do you have a chance to fill me in? What's your status here?
Okay. Sorry. Yeah. I found P1, P2, and P3. I haven't. I guess I found, but the P1, P2, and P3. I haven't found the magnetic field to the right of Y2. No.
To the right of, okay, yeah. So you're not done with part B yet. That's fine. I'm gonna close the rooms in here pretty soon, like maybe 45 seconds or so after I do this next round. Okay. All right, I'm gonna go to the next room. Okay, are we doing good over here?
Yeah.
Yeah.
I'm gonna close the room soon, so I'm just doing another pass through here. So letting you guys know.
Okay.
Hey, so I'm gonna close the room soon, so just letting you guys know. Is there any questions here?
No, no questions right now.
Okay, any questions here?
No questions, Professor.
All right, I'm gonna close the room soon here in a second.
Yeah,
Okay, any questions here?
I think 2 pi still. Or no, 1D is right and then 3D for the beach one. Hi. Yeah,
Any questions here or no?
No,
I
we're
think we
fine.
got it.
Okay, I'm gonna close the rooms in like 15 seconds. Okay, just letting you guys know.
Okay, Professor.
I was muted. We will go over the question once everybody gets in here. So hopefully it will be the same as kind of what you guys already have. So a couple more people, waiting on a couple more people here. Let's see who's left. Sarah, Alberto, Tatiana. Okay, rooms will auto close here in like 5 seconds. Okay, that's everybody. All right, so I'll go ahead and share the screen now. Back into Paint here, the almighty Paint. All right, so let's take a look at what we can do here for these different points. So for P1, the magnetic field due to wire 1 is down, and so I'll give it a minus sign. So B1 is minus, and I'll do this one-dimensionally. I won't write the y unit vector y hat. So B1 is going to be minus mu 0 I over 2 pi r, and r here is going to be 3D minus 1D. Okay. The distance from wire 1 to the point P1 is 2D. It's 2D. So I'll put 2D here. Now, how about B2? B2 is positive, it's pointing up due to wire 2, and it's a distance 4D. Okay, distance 4D. Add these two together to get B total. What you're going to get is that this thing is minus mu 0 I over 8 pi d. In the direction, because it's negative, it will be in the negative y hat direction, right? So just tag on a y hat there since it's already negative, so it's going to be pointing down. That is for P1. For P2, we have B1. Here we're looking at the point P2, which is right in the middle. So both of these guys happen to, if you use the right-hand rule, they're both pointing in the same direction. So out of comes up in the middle, and into also comes up in the middle. So they're both positive. So mu 0 I over 2 pi d. And that is also equal to B2. They are the same magnitude and the same direction, so they are identical. So that means B total is going to be twice as much, because we're adding B1 plus B2. So we have mu 0 I over, over pi d. And for P3, we have B1 equals mu 0 I over 2 pi, and then for P3, the distance is 3d. For B2, we have mu 0 I, and B2 is negative since it points downward. Again, just use the right-hand rule there. It's pointing down at the point P3. And at the point P3, B1 is pointing up, right-hand rule. 2 pi times just d here for B2. And this, of course, means the total, the sum of these two, is going to be, it's a sixth minus a third, so that's going to be a negative sixth. So mu 0 I, or excuse me, oh no, yeah, that's right. Minus, I do that right? Yeah, I think that's correct. Yeah, so minus a sixth pi d. Let me just double check that. Oh no, excuse me. What am I doing? It's minus a half, not minus a third. So it's going to come out to 1/3 here. So 1/6 minus a half. A half is 3/6, right? So you're going to end up with negative 2/6 with it, which is negative 1/3. There we go. All right, and then finally for part B here, we'll go ahead and switch the colors up on it. At some point, let's call it Px, which is a distance x to the right of wire 2. B1 will be equal to mu 0 I over 2 pi, and then x, or excuse me, r, the distance from wire 1 out to some point x, is going to end up being 2d plus x, since x is measured from wire 2 to the right. So it'd be 2d plus x. And then B2 is nice and easy. It's just divided by x, right? So mu 0, 2 pi. Since x is the distance that we are away from wire 2, mu 0 I over 2 pi r is just going to be mu 0 I over 2 pi x. R equals x. And then B total here will be the sum of these two. And you can actually go ahead and get a common denominator on that if you'd like. I'll just quote you the answer after the common denominator is found, because I want you guys to just work it out yourselves. And I know a lot of people actually weren't able to do part B here. You should go back and finish it off. So minus mu 0 ID over pi d squared plus, x squared minus d squared. So you should be able to work that out. Actually, oh, that's right. Ah, that's right. That's right. Okay, so I do see there's some chats. Give me 1 second. In the book, actually, this answer here is quoted to you for when x is measured from the positive, sorry, from this point right here, the origin. So they may measure x from the origin, not from wire 2. So I gave an answer where x was measured from wire 2. You can get a common denominator there too. And as a matter of fact, you should have the same physics no matter where you stick the origin of your coordinate system, right? So it might be interesting for you guys, if you want, to take these and get a common denominator. And then compare that formula with this formula here. So compare with this formula and make sure that the physics is the same. So if you were to plug in the distances for P3, make sure you come out with the answer, you know, minus mu 0 I over 3 pi d, right? All right, let's take a look at the chats now. Okay, Professor, shouldn't P1 be 1/4, not 1/8? Did I mess that one up too? Yeah, it's an eighth. Oh, well, it's an eighth minus a quarter though, right? So a quarter is 2/8. So it's an eighth minus 2/8 is negative, excuse me, negative 1/8. Let me go ahead and check the answer here on that. No, I have that one correct. Minus 1/8. Yeah, at P1. Okay, so there we go. There's our answer there. We should honestly be able to check this formula for every value of x. You know, we can plug in x is minus 2d, for example. And according to this formula, x is minus 3d. If we plug in x is minus 3d, that would be the point P1. So x equals minus 3d is right here. If we were to plug in x equals 2d, or rather, let's say x equals 0. X equals 0 would be this one, right? And this one right here is x equals 2d, right? In the Halloween spirit, we can box these answers in orange in addition to black. There we go. Okay, so you just always, whenever you get an answer, check that it makes sense, check that it reproduces the answer that you got, you know, from some easier question. All right, we're going to move on from that example now. And we are going to talk about the force between current carrying wires or conductors. Forces between, and we don't have much time left. We only have about 20 minutes left. And so on these next couple of topics, we might go a little bit quicker just to make sure we can cover everything so you guys are ready. We might not have enough time to cover magnetic materials, but I will make sure that there aren't too many difficult problems on magnetic materials. If they do show up, they'll be on the second example, and there will be at least one, okay? Because I do want you guys to read up on that and understand that. Forces between current carrying conductors. Okay, so what do we have here? Well, we have some conductors which carry current. Okay, actually I should just use this line drawing function so they're nice and parallel here. Vertical and parallel, there we go, that's good enough. So we have the current I1 and the current I2. And these two currents give rise to magnetic fields, right, which circulate around each of these wires. And I will now use two colors, okay? So the green that you're seeing now, this is the magnetic field due to I1. We'll call it B1. And over here, of course, coming out of the page, of course, there are an equal number of dots and crosses, so maybe I'll put that one in there right on top of the I1 there. Maybe we can just move that out for a second. Let's take that and move it out for a second. And then we can find a nice space right there. There we go. And then maybe I'll use a slightly different green here. And the magnetic field here, due to this current carrying wire, will also be into the board. So hopefully you can distinguish between these two colors. Let me know if you want me to change the colors here, or if this is good enough. You know, maybe there's somebody who's colorblind in the class and they can't really distinguish between these two colors. Just let me know. I can change that up. Okay, so this is what we have here. So then this one here we'll call B2. Right? And the important thing is that the magnetic field that generates the force on these wires is not the magnetic field of the wire that the force is being exerted on, but it's the magnetic field of the other wire that generates the force on the wire. So let me spell that out a little bit better here. So there is a magnetic field located at this wire here, which carries current I1, and it is due to the current I2. And so the magnetic field here is B2, not B1. If we were to just blindly go through a problem like this, we might make a mistake and say like, oh, the magnetic field goes like 1 over R. And so the force on the wire with current I1 flowing would be infinity because the magnetic field is infinite there, right? The magnetic field goes like 1 over R. And so if I plug in R equals 0, then I have an infinite force there. Well, of course, that would not make sense because we have wires that have current in them, right? And they're not experiencing infinite forces. So the correct way to go about this is to recognize that the magnetic field of the other wire is the one that causes the force. So it's not a self-interaction, it's an interaction between two objects at a distance, right? And what's mediating that force is the magnetic field. Okay, so this is B1 here. I never actually wrote that this was B1. There it is. Okay, so we kind of know what's going on now. Let's figure out the direction of the force on wire 1, which carries current I1. So at wire 1, the magnetic field is going into the board. We have to remember that the force on a current carrying wire is ILB, but the magnetic force on the wire which carries current I1 would depend on I1 and the length of the wire, L1, right? But as you can see here, It is the magnetic field B2 which generates the magnetic force on wire 1. And so we must put B2 here. Likewise, the magnetic force, and let me actually go ahead and let's drop this M subscript. We know it's the magnetic force. Let's be super careful here. This is the force on 1 due to 2. So this is F12. What is the force on 2 due to 1? What is the force on 2 due to 1? That's a question for you guys to answer. What is the force on 2 due to 1? What is the force on 2 due to 1? We have a chat. I2, L2, B1. I like it. So I2, L2, B1. Exactly. So I2 is the current that is flowing in the magnetic field B1. So it is I2 times the length there for that current of the wire times B1. You can see as I was writing it there, I was getting a little bit confused myself saying the numbers out loud. But there it is. It's correct on your screen here. This is correct. And you must wonder at this point, you should definitely be questioning what's going on here at this point. I have 2 current carrying wires, and the forces on these 2 wires do not appear to be equal. At first glance, these 2 forces seem wildly different, right? We have I1, B2, we have I2, B1, right? And L1 and L2. There's no way Newton's third law is going to be valid here, right? Well, before we even get into that, let's think about the direction of the force, okay? Let's think about the direction of the force. So we got to use the right-hand rule. The Lorentz force says stick your fingers in the direction of the flow of charge or the velocity of the charge. Let's take a look at I1 or wire 1. If I stick my fingers like so in the upward direction, everybody get your right hands out, stick your fingers in the upward direction, and then curl your fingers into the screen. So from your guys' perspective, it looks like I'm curling my fingers towards you, but I'm actually curling my fingers in towards my screen. And that tells me that the magnetic force is to the left on wire 1. Magnetic force is to the left on wire 1. So this is F on 1 due to 2, F12. Okay. All right. How about wire 2? Current is now going down, so I have to contort my arm to show you. I stick my fingers down and I curl them into the screen like this, right? And my thumb points to the right. So the force is in this direction. This is F21, like so. Okay, so that's kind of nice because Newton's third law does say equal and opposite forces, right? So certainly we have opposite forces here. These forces are in opposite directions. But what the heck is going on with their magnitudes, right? I'm looking at this thing, I'm thinking, there's no way these are going to add up, right? There's no way they're going to be equal in magnitude. But it turns out that B2, let's maybe use green. B2 is the lime green, so B2 is mu 0 I2 divided by 2 pi, let's call it d. Let's say the distance, let's do it in pink here. The distance between the two wires, let's call it d. Right? And B1 is mu 0 I1 over 2 pi d. And wait a minute, now we're starting to see things match up, right? Because now we have I1 and I2 in the same expression, right? I1 and I2 in the second expression as well. Now things actually are starting to look better. So F12 is mu 0 over 2 pi. That's the constant piece. And then we have I1, I2 divided by, times L1. Let's leave that till the end. So divide by D and then times L1 here. Now, okay, that is peculiar. L1 didn't cancel out, right? L is assumed to be infinite. What's going on here, right? We can't have infinity here for our answer. Well, that kind of makes sense that, okay, the magnitude of F12 and F21 looks awfully similar, but they're not precisely equal to each other. And the reason they're not precisely equal is because we have infinities floating around in our expression. So L1 and L2 are both infinite. And so that's why they're showing up in the expression as not equal, right? Because you have to be very careful when you're handling infinities in your equations. So what we should do is we should talk about force per unit length. So F12 divided by L1 is mu 0 over 2 pi I1, I2 divided by D, right? And F21 divided by L2 is equal to mu 0 over 2 pi. And so we can see now that for any two wires of finite length, the force per unit length will be equal and opposite. Or excuse me, I meant to say any two wires of infinite length, the force per unit length will be equal. And of course, if you have finite wires of different lengths, it doesn't even matter what their lengths are. If they have different lengths or the same lengths, of course, Newton's third law will 100% hold. The proof of that, we will not prove that. I'll leave the proof of that up to you guys. It's a little bit, maybe it's a little bit out of the scope of this class even to show that that's going to hold. Might have to break out a little bit more math to show that, but indeed, it has to be true. Just based on the simple fact that every force that you experience in your everyday life besides gravity is essentially the electromagnetic force. And so Newton figured out Newton's third law without knowing anything about electricity and magnetism. And of course, all of the forces that Newton knew about were, of course, obeying his third law. Okay, so no violation of the third law here. Another really interesting thing about these equations here is the fact that it's a 1 over d dependence. 1 over d dependence, of course, not 1 over r squared, but 1 over d. So that's kind of peculiar. And in fact, that has to do with, of course, the fact that we assumed the wires were infinite. So the denominator here of these expressions would be a little bit more complex in the case of finite wires. It's definitely something that we can do. Matter of fact, we did that question basically earlier We did take a look at a finite wire, and then we took limits as a went to infinity. But basically what we would do is we'd figure out the magnetic field at all of the points on the wire, and then calculate the magnetic force and sum up from all those contributions, right? It'd be an integral, it'd be a nasty expression, it'd be a nasty problem to go through. That's why we're not going to do it. We're just going to trust Newton's third law holds because it's always held for us in the past. And we'll wait until quantum mechanics comes around and we have to throw away the notion of force, right? So Newton's laws do not apply in the quantum world anymore because it's too difficult to define what you mean by force. Okay, so that question is now over and done with. Let us do a simple example here. So we'll take two parallel wires with 15,000 amps of current flowing in opposite directions. Excuse me. Let's go ahead and extend this out in opposite directions. What force per unit length do they exert on each other? Okay, and wires with current flowing in opposite directions and separated by a distance 4.5 millimeters. What's the force per unit length that they exert on each other? Let's get a quick picture. Go ahead and start working on this question. I'll let you guys work solo on this one. Go ahead and punch your answers into the chat when you get them. Current flowing in this direction and current flowing in this direction. What kind of force is this going to be? Is it going to be repulsive or attractive? That's maybe another follow-up question. We have a chat, 67.5 newtons repulsive. See if people agree. While you guys are working on that, let me let me go blow my nose real quick. Be right back. Okay, I'm back. Yeah, 10,000. That's the correct answer there. I promised 2 examples using the Biot-Savart law. And so, of course, the story of this class is, can we remember formulas? So I will now ask you guys to state the Biot-Savart law without looking it up in your notes. Just state it to yourself. This question here, force per unit length, is exactly what we just did. It's going to be 15,000 squared times 4 pi times 10 to the minus 7 divided by 2 pi divided by the distance, 0.0045. When you crunch the numbers on this, you get 10 to the 4th Newton per meter. So Biot-Savart law, Biot-Savart law. The force is, of course, repulsive because these currents are in opposite directions. So you will have always repulsive force when currents are in opposite directions, and always attractive when the currents are in the same direction. We can go ahead and write that down too, because it's useful to remember. Attractive force when currents are in the same direction. Repulsive force when currents are in the opposite direction. Yeah. Okay. All right, so I've given you enough time to kind of remember the Biot-Savart law. Give me 1 second. Ah, that's what I did, okay. Oops. There we go. We're going to go ahead and use Biot-Savart to solve for the magnetic field due to a ring of current. So use Biot-Savart. To get B at P. Okay, Biot-Savart. All right, what's Biot-Savart? Well, Biot-Savart tells us about the magnetic field, right? All right, so let's say dB equals what? You guys tell me without looking it up, okay? If you're confident that you remember what it is, don't say anything. If you're not confident, those are the people I want to kind of to say what they think it is in chat, so that way I really know that they're thinking about it and they're trying to remember it. I think it's a good way to kind of help yourself remember. So the pressure is on a little bit here. So what is the Biot-Savart law? It looks like we're going to have to end pretty soon here. So we'll try and cover Ampere's law before we go, and then you guys will have to maybe do the last 2 sections of the book on your own. So Biot-Savart. Biot-Savart, what's the first part of the Biot-Savart? There's an I on top. I like it. There's an I on top up here, right? It has to do with the current. Current, more magnetic field. What else? How about some constants? How about some constants out front? What are the constants out front? We've seen mu over 4 pi. We've seen mu over 2 pi. We've seen mu over pi, actually, in one problem we also saw. Mu naught over r pi. Oh, over 4 pi. Yeah. Mu naught over 4 pi. I like it. So mu naught over 4 pi. Okay, and then it's I over something, right? So I times something something divided by something something, right? What kind of field equations do we like to have? Like Newton's law of gravity is like, what does that depend on? How about Coulomb's law? What does that depend on? 1 over what? Probably an r down there, divided by r squared. Good, Alberto, nice. Divided by r squared. All right, now I'm looking at the diagram and I'm thinking, oh my God, this is a test. I don't remember what the heck to do. I better just look at the diagram and try and figure it out, right? I look over here at the diagram. I see a DL. Where does DL go? Tien says DL on top. Does everybody agree with that? Should DL be on top or should it be on bottom? Should be on top. Okay, DL. Let's write it up here. Let's see. Okay. I know it's a vector. I have a vector on the left side, right? I have to have a vector on the right side. All right, is that it? Or is there something else? Well, I see an X, I see an A, I see a theta, I see an R, I see an R hat, times R hat, times R, cross R hat. I like cross product because I think I remember that whenever we're dealing with magnetic fields, there's always a cross product, right? There's always a cross product with magnetic fields. Don't forget that. There's always a cross product. If there's no cross product, there's a sine theta because you've taken the magnitude of a cross product, okay? So there it is. That's the Biot-Savart law in all its glory right there. So what we need to do is figure out how to integrate this thing, because b at the point P is going to be equal to the integral of this expression here. So we'll go mu0 over 4 pi integral, well, we can bring the I out as well because the I is constant, dl cross r hat over r squared. All right, well, there's some nice symmetry here, right? There's some nice symmetry. For example, if I do take the magnitude of this cross product, I know that only the component along the x direction matters, right? Because there's a y component here. Here's the y component. But the thing is that's from a dl vector, which is up top. There's also a dl vector, which is down bottom. And dy would be in the opposite direction down there, right? And since the current flow here is uniform and we have cylindrical symmetry, then of course all the y components will cancel out, right? All the y components have to cancel by the symmetry of this problem. And so what happens is we only need to keep track of the x component so that we can take the magnitude here and just multiply by x hat. That's the correct direction, right? That's the correct direction because all the y components cancel. So the magnitude here of this, and I better switch colors before it gets too dull here. The magnitude of this is dl times sine of theta, right? dl times sine of the angle between r hat and dl. Well, guess what? I'm looking at the diagram. I see DL and I see R hat, right? Where's my mouse at? There it is, right there. Look, they're at right angles. They're at right angles to each other. All around that ring, they'll always be at right angles. Okay, see that? They're always going to be at a right angle. Okay. Or wait a minute, sorry. Am I saying that correctly? Are they going to be at right angles? Yeah, of course they're going to be at right angles. Yeah, because DL is in the along the z-axis, and r hat is in the x the y-x plane, right? I got a little tripped up there because they're making like a slight angle in another direction, but no, they are indeed at a right angle. And so sine theta is 1 here. Okay, so integral over dl, and we have r squared in the denominator, so we better write r in terms of like x and a, right? Let's go ahead and do that. So mu 0 I over 4 pi, and we're going to go ahead and integral. We're going to integrate dl. We want to replace r with x squared plus a squared. We can get that from the triangle here, right? So let's write it over here. Here's r, x, and here's a. And here's the angle theta. You know, and maybe I probably shouldn't have said sine theta here. They kind of switched their notation up. Maybe I should have said sine phi, because this is the angle between dl and r hat. So maybe next time I better pay more attention to that. So this angle theta that they've labeled here is different. So x squared plus a squared for r squared. Is there anything else that we need to do here? Well, we need to set up bounds for the integration. Well, dl I can rewrite as a d theta, and then I can integrate theta from 0 to 2 pi, right? So I can just get rid of the dl here, and we're integrating at an angle here, right? So we're integrating at an angle here, at an angle theta. So when you integrate like this, from 0 to 2 pi here of this thing, well, we're integrating over theta. So a over x squared plus a squared does not depend on what is in the integrand there. So pull it out. Mu 0 I over 4 pi. A over x squared plus a squared. And then times a 2 pi up top. And it's as simple as that for the integration, which is really nice. We had some nice symmetry there. Oh, wait a minute. Wait a minute. Aha. I made a slight mistake here. All the way back here. In order to get the x component, we have to multiply by cosine theta. So we have to multiply by cosine theta in order to get the x component here. Right? X component is going to be b cosine theta. Y component is going to be b sine theta. Right? So I forgot a little cosine theta here. So I jumped the gun there a little bit. So maybe we should take a step back. But it turns out cosine theta, you just read it off from the triangle. Cosine theta is a over r. So a over x squared plus a squared to the 1/2 power. And again, that doesn't depend on the integral. So we just need to correct this real quick. It should be a squared over x squared plus a squared to the 3/2 power. Sorry about that. So this should be squared and this should be 3/2 power right here. But again, none of that depends on the integral there. None of that depends on the integral, and it all just pulls right out of the integral, and we can integrate over theta since we've replaced cosine theta with what it is in terms of the length variables. We don't need to worry about it in the integration over the angular theta. Okay, so now we do have the correct expression there. So I just forgot the cosine theta there. So fix that up in your notes. Again, the reason the cosine theta is there is look at the triangle over here on the right side, right? Look at the triangle over here. Cosine theta times dB is dBx. So dBx is equal to dB cosine theta. Right? So as soon as I put times x hat, I should have multiplied by cosine theta. Okay, sorry about that. There it is. That's what we've got now. We can simplify as much as possible here. We can cancel a 2 with the 4 to make a 2. We cancel the pi's. And what are we left with here? Mu 0 I a squared over 2 x squared plus a squared to the 3/2 power. Okay. Any questions about that? We're a bit over time, so let me quickly cover Ampere's law. We'll do it quick. Ampere's law is just like Gauss's law, except slightly different. Okay, so historically, Ampere's law, had a mistake in it. It didn't work in general. Maxwell had to correct the law so that it worked in cases where you had time-changing magnetic and electric fields. So Ampere's law works in static situations. So only for static fields, which means they don't depend on time. No time dependence. And what it says is a closed loop integral B dot dl. In the past, we used R, we used dr, like F dot dr or E dot dr, right? We're going to use dl here because Biot-Savart law has that. You know, there's a lot of R's and L's everywhere. So I'm just going to follow the book notation to a T on this one and just keep it L here. So B dot dl is equal to mu 0 times I enclosed. Or I think we usually write in. I was writing like Q in, so we'll write I in here. So B dot dl equals mu 0 I in. And we could just quickly verify this for a circular path. If I take a circular path like this around a current carrying wire, current I, and the magnetic field at these points are tangent around the circle. So these are the magnetic fields. That's circulating around that wire. Where's my mouse? There it is. DL is measured along the circle here, right? So this is DL right here. So it's a little vector there with magnitude equal to the small little segment of the circle. If I do that, I can plug in for B, I can plug in mu 0 I over 2 pi r. And of course, the direction of the magnetic field vector is in the theta hat direction. Theta hat is a vector which circulates around the r hat vector. Integral over a closed region, dot product, magnitude of dl. dl is also in the theta hat direction, and so the dot product between theta hat and theta hat would be 0. And that is supposedly equal to mu naught times I on the right hand side. The only I enclosed inside of this loop here that penetrates through the loop right there in the center is the current I. Okay, so dot product goes to 1 between two unit vectors that are the same there. So like this, dl, we integrate this thing. And this thing is integrated over a path which is equal to the circumference, or sorry, is integrated along a path at a fixed radius. So the magnetic field is the same everywhere, and it's around the circumference of the circle. So we can pull the magnetic field outside of the integral here because r is a fixed value, and we can integrate from 0 to 2 pi, where dl is r d theta, and again the r can pull out again, and we can just cancel. In fact, we just cancel the r's there like that. And then this integral right here is 2 pi, and so we cancel 2 pi's, and it does indeed equal mu 0 I. So Ampere's law appears to be working. Now you can use Ampere's law to figure out the magnetic field in situations where you have symmetry. For example, if you have a cylinder like so, and these examples are in the book, I can draw a closed path here. If there's current flowing like this, right? There's current flowing like this, I can draw a path like this going around counterclockwise, and I can calculate the magnetic field inside the conductor, inside the conducting wire, and outside. And what I see is kind of similar behavior to what I saw in electricity and magnetism, whereas something like proportional to R here and something like proportional to 1 over R over here, or 1 over R squared, depending on the actual symmetry in the problem. Okay, so you can have all kinds of different things going on depending on the symmetry. Now, oftentimes things have to be cylindrically symmetric, but there are some cases where you have planar symmetry. For example, for a solenoid, you actually take advantage of planar symmetry. For a solenoid, the magnetic field, in other words, a coil of wire, solenoid is another word for coil of wire, you get that the magnetic field is mu 0 I times lowercase n, and lowercase n is turn density. So it's the number of turns per unit length. Number of turns per unit length. Okay. And the nice thing about a solenoid, and this example is perfectly solved out, it's great, I've already seen it in the book. It's a really good explanation. Check it out. The nice thing about a solenoid is that it has a very uniform magnetic field in the middle. And if you have an infinitely long solenoid, then the magnetic field is uniform. Just like if you have an infinite parallel plate capacitor, the electric field is uniform, right? So same kind of thing if you have an infinite solenoid. Okay, so let me give you some page numbers and stuff that I would expect you to go and study on your own. So 28.6 is what I just introduced. That's Ampere's law. 28.7 and 28.8. Those are the parts you need to do yourself. So do yourself. And really go through, make sure you understand all of the examples in 28.7. All examples in 28.7. I would say that's the most important, but really you should go through all the examples in every section of the chapter, right? And make sure you understand all of them. the more problems that you go through and study, the harder it is to be surprised by a question, right? Like that shows up on the test. Anyways, we're going to end it there. I will get your guys' homework part 2 posted very shortly. Homework part 1 is still due though, right? Tomorrow. So probably nobody's even thinking about part 2 yet, but I have not posted that yet. So I will get that up soon. All right, we're going to go ahead and end the call, and then I'll go ahead and answer any questions you guys have. Or sorry, I'm going to end the recording.